Okay, so we're at the Computer History Museum. It is March 20th, 2014, and I'm Doug Fairbairn. I'm here with Robert Brayton, who is Professor Emeritus at UC Berkeley and previously employed for at least a couple of decades at IBM. And we're going to learn about his life, his career, and the contents of some of those 450 technical papers and 10 books which he has had a role in the authorship of.
The contents.
So we won't quiz you on every one, but
okay.
We'll make sure that you actually had some part in some of those. So I understand you were born in early years, was spent in Ames, Iowa. It must have been a farming town, or
No, well, I was born in Iowa, and when I was in 7th grade, I came to Ames.
Okay.
And Ames is not really a farming town because there's a huge university there, Iowa State University. And I lived about 7 blocks away from the university, so it wasn't kind of typical.
So it wasn't
Iowan.
So before 7th grade, I mean, where were you?
Well, a little town of Humboldt, Iowa. Ever heard of it? Well,
what year were you born?
1933.
Right in the middle of the Depression.
Yeah. Fortunately, my dad was a teacher, and so those jobs continued. But I think they cut the pay by half or something during the years. But,
interesting. So there was an educational bent in the family from the very beginning. Did you have brothers and?
Well, not really. My dad grew up on a farm, and he was in agriculture.
Oh, okay.
And even though he lived in Ames, there was no connection.
But he was a teacher anyway. He
had actually was a high school teacher.
So there was some value of education, or recognition of the value of education.
Yeah, I guess so. But actually, the biggest influence was in the neighborhood that I lived in, Ames. There are a lot of professors living there and children of the professors.
Interesting.
And that probably swayed me a little bit.
University town, and
university town.
Yeah. So you went to high school there. When did you discover your interest in technology, mathematics, computer? You know, what was it like in high school? What did you think about going to? Was it Iowa State?
I didn't think about it, but most of my friends went there, and it was so easy to go to down the street.
I'm sorry, was it University of Iowa or
Iowa State?
Iowa State, right? Okay.
Yeah, and
so that was sort of a foregone conclusion that if you were going.
Yeah, I didn't even think about it. I didn't take any SATs. I didn't apply any place else. I think in August I sent in a letter saying, I wanted to attend, and that was it. There was no pressure.
No entry
in those days.
Entry hurdles to get through.
Yeah,
but in high school, did you know what do you develop an interest in any subject or
basketball?
Basketball. See, you're a tall guy.
Well, for back then I was 6 foot, and I think we had a center on our basketball team that was 6'2". But that was my main interest in that.
So you were fully qualified as a basketball player at your height.
Yeah. But I think the thing about basketball was the Iowa State gymnasium was right down the street. So every Saturday we could go in and get some scratch games up.
Oh, great.
We played every Saturday. So.
Yeah.
So that was my main passion in high school.
Now, did you have siblings?
Yeah, one brother older and one brother younger. Yeah, and they both went into the ag business.
Okay. So you went to Ames. Went to Iowa State. Tell me about your time there and how you got steered in the direction of computing and mathematics.
Yeah. Well, I in high school I kind of got B's and C's and everything else, but in math I got A's. And when I started at university, I thought, well, I want to be an engineer. I don't want to be a mathematician per se. I wanted to earn some money, and so I said, okay, I'll do engineering. And engineering was a big thing at Iowa State because it was originally a tech school. And they had a good engineering program. So I started on aeronautical engineering.
It was big at that
And,
time, yeah.
learned that that didn't sound, it wasn't going to be as interesting as it sounded.
Mhm.
So I switched to mechanical engineering.
This is the
And
early 50s you were going.
I started in 51, and
Yeah.
so 51, 52. I was switching around the engineering disciplines, and then I took my first electrical engineering course,
Mhm.
which was kind of eye-opening. The fact that you can write down Kirchhoff's laws and equations and then solve them and so forth was
Mhm.
very impressive to me. It was very mathematical, which I liked.
Mhm.
So I took that as a double major for a while, and then so as a double major, I had to take 5 years. But in my 5th year, I decided I wanted to do more math and physics, so I dropped the ME and just did math and physics and the electrical.
So, in your electrical engineering work, was it mainly equipment? I mean, motors and generators? Was it tubes? Was it?
Well, transistors were just coming in. So
Yeah. That was,
about 53, they started teaching about transistors.
well, that's pretty early for
Yeah, I think when did transistors were they invented?
48, 49.
Yeah. So it began getting in the textbooks around 53, 54, and so that was great and eye-opening. And I was, at the beginning, I was kind of leery about getting into electrical engineering because my view of it was that you had to know how to solder and you had all these ham radio guys who knew much more than I did. But then I got into the circuits course, and I found that was great fun, so that was good.
Interesting.
But we did have, motors and generators in a big lab with huge machines in it for generating things like that. I don't think they're there anymore. But
Now, did you have any professors that were really mentors that steered you in one direction or another, or how did that?
Not so much. I had good professors and everything. I remember one professor who was a mechanical engineering professor, and I don't think he was a mentor or so, but he was such a good professor. His name was Harold Black, I think.
Mm-hmm.
They have a building named after him now, but I took thermodynamics from him, and that was a great.
They have a building named after him. He must have impressed
somebody
more than you.
Yeah. So thermodynamics, and actually if you go back into thermodynamics, there's something called the Brayton heat cycle.
Ah.
And that's like a 10th cousin 5 times removed.
Some other Brayton that...
Well, it's the same tree, but it branched off about 10 generations
Interesting.
ago. Yeah. Anyway,
you had some of that in your blood anyway, huh?
Yeah, something. Yeah. So, yeah. So that was, my background at Iowa State was getting exposed to all these engineering disciplines, so it wasn't a waste of time to take mechanical and aeronautical.
So at that time, what did you envision as far as a job or career? Did you assume you would just go off and work in one of these engineering fields, or?
At some point in time, I thought, well, maybe I'll go to graduate school.
Mm-hmm.
And but I was in ROTC, so I had to go in the Army for 6 months.
Mm-hmm.
Fortunately, at the time, the Korean War was ending, so
Right.
ROTC obligation was cut from 2 years to 6 months,
Uh-huh.
and then 7 years reserve. So I went to work for Sperry ran UNIVAC,
Mm-hmm.
and got kind of using computers there. And
You mean after your ROTC commitment?
yeah,
Uh-huh.
no, before.
Before, okay.
I was at Sperry for about 6 months, and then ROTC Army for another 6 months, and then in the middle of that, I started applying to graduate schools
Okay.
and got admitted with money at MIT, so I chose MIT to go.
So at Sperry, were they building computers at this time?
Yeah,
and what was?
I was on a team that was building an onboard computer for ICBM,
Hmm.
and our little group was designing the memory. So the memories back then were these iron cores.
Yeah, cores. Core memory.
Core memory, yeah. And they had the rows and columns, and then they had the sense wire going through. And we had to build a good amplifier for the sense wire that would sense the switching of the magnetic positions on the cores. And so that was good.
And this is, you were using transistors at this point, is
yes, definitely, yeah. And fortunately back then, when you design something, you wanted to get it right. Instead of simulating like we do nowadays, we would build it on a board, and then we'd put our finger on something to, add a little capacitance here and there, and so forth, to see where we go.
Fine tune it.
Yeah. So.
So do you remember where those transistors came from? I mean, there weren't very many companies building transistors back then.
I don't know. They came from the supplier.
Just curious. Yeah.
I was concerned,
so. All right, so you had some introduction at least to electronic design and so forth. And when was your first introduction to computers?
Well, let's see. At Iowa State, we didn't have any, but I began to get interested in them, I guess, because they were just coming out and being used. And so when I took the job at Sperry, they had computers because they made the UNIVAC computer back then. And so we would, I was trying to think last night, what were we computing on it? Because I remember writing some programs, putting them on punch paper tape, and then running them through the computer, and it would do something. But I don't know what we were programming at the time. Can't remember. I don't think we were simulating circuits.
Yeah. So they, downstairs in the museum, we have, I don't know how much of a piece of the Sperry computer, because it was used, or UNIVAC, it was used in the prediction of the outcome of the 1952 election.
Oh.
And
yeah, well, that's probably one of the ones, or maybe a generation later.
So we ought to take a look down there and see.
In I think it was 56, I started this 6-month duty for Sperry, and I remember these big rolls of paper tapes.
Yeah, it might have been 56, but that would have been Eisenhower second. We'll have to take a look.
Yeah.
Is there any memory you have of how you chose MIT other than they gave you money, or what were the other schools you applied to or were considering?
I wanted to go to Boston, so I applied to Harvard, and MIT and Harvard admitted me, but they weren't giving me any money, at least at the admission. So I went to MIT, and I had a background as an engineer.
Right.
Now the difference was that I had decided that what was limiting what I learned about was my background in mathematics. I only had the kind of engineering mathematics, so I entered MIT. I applied to MIT and Harvard in mathematics, and so I got admitted to the math department. Of course, they didn't have any computer science departments back then, but even at that time, I was interested in computers. And but I just enrolled in general mathematics.
So, in looking at your future work, it looks like that played a critical role in the work that came later. Is it was heavily mathematics based, right?
Because I had the EE background enough to kind of master what was going on there, but mathematics. So if you look at my work over the years, it's been kind of mathematical based a little bit, although applied to computers or electrical things.
So you entered MIT in 56, 57?
57, fall of 57, in the math department, and I was coming in as a engineering undergraduate and starting math, and so I was a little bit behind in the math. So the first year I was there at graduate school, I was basically trying to catch up with all the senior course mathematics that was taken by the math graduates.
Mm-hmm.
So that was, you know.
That was the same year, at the same time Sputnik was launched, right? When you were.
Well, Sputnik, what did they come in? I think it was more like 59 or 60. Sputnik was.
That was 57, but.
Well, you might be right, actually.
Anyway, so I was wondering if there was any particular memory you had of that. So you entered the math department and you had graduated with a double major and then gone in and were going to pursue a PhD. I presume that was your goal, right?
That was it.
And a PhD in mathematics, was that the path that you were on?
Yeah. Well, and I came in and I guess I told them I was interested in computers and computing and all of that. And so at the time there were people in the math department that were in logic and recursive function theory and well, let's see. Oh, a guy named Hartley Rogers, which is in logic and so forth. So I came in there and was kind of interested in that. And the research assistantship they offered me was partly double E and partly mathematics. And it was in the group that was run by John McCarthy and
Oh yeah.
and I forget his name now. Michael Minsky.
Oh, Mike Minsky, yeah.
Yeah.
Minsky.
Marvin Minsky.
Marvin Minsky.
Yeah. And so I was in their research group, and there was about 7 or 8 of us, graduate students, and McCarthy and Minsky and a few more senior guys, and then the year after, in the fall of '58, McCarthy had come back and had this idea about the Lisp programming language. So our group started working on that and implementing it. And so the next three years was doing, that was my research.
Is that what you did your PhD on?
No.
Okay. That was just your research work leading up to that.
So this was called AI back then.
Yeah,
And,
yeah. I mean, I actually worked in the Stanford AI lab as an undergraduate, just doing technician work and so forth that McCarthy was running after he'd come out to Stanford.
Yeah.
So anyway, so you were.
So I worked on that, but I was in the math department, and I took some courses in math that I got very interested in, and I thought, well, AI doesn't have much of a future. I don't want to put my career there, so I just I did analysis, and I worked for a professor, Norman Levinson, who was a student of Norbert Wiener. You know Wiener?
Yeah, I don't.
He's famous around MIT. That's the story. But anyway, and that was in pure mathematics analysis, basically. Differential equations was what I specialized in. So I did that as a thesis, but my research assistantship was in the Lisp group.
I see.
And
so you got a little bit of both. You got into the computing
and it
world.
Was great fun. Yeah, great fun. And my job in Lisp was to write their compiler.
And on what machine was that being done?
That was a IBM initially. Let's see. It was before 704, I think. So I'm not sure what they had before that. But I remember it was in a big,
computer room.
Cooled, air conditioned, everything, and you'd bring your cards and card deck in and put it there and wait overnight and come back and you read the result and
find out where your bugs were and
you forgot a comma here, and then you'd go off and do it again. So actually, it trained you to be very careful.
Yes.
About writing your program and double checking and everything, because you didn't want to spend it night after night and night fixing stupid things.
Right.
Yeah. So, so that was a great job, great fun, and a lot of the work I've done, since I got out, had to do you could say it's had to do with compiling something.
Mm-hmm.
And so this was the first taste of that kind of.
Interesting. So, any special memories of your time at MIT? What people that had the most impact, or aha moments, or something that steered you in a particular direction? Is there anything that?
No, it was just a good time.
Just a good time, and learned a lot.
I enjoyed all the courses.
Yeah.
MIT was a great place. There was Norbert Wiener, and there all the. Oh, there was also a young professor there who was, this book, A Beautiful Mind.
Mm-hmm. Yeah.
Yeah. What's his name?
Yeah, I don't remember the name, but
John Nash.
Yes.
Anyway, he was a young instructor.
No kidding.
There, and we would see him around the hall. I never even talked to him, but
yeah.
But the rumor was he was a pretty bright guy, and then he just suddenly disappeared. And of course, you know the story of him. He was just a great mind and solved. He got a Nobel Prize in economics, but he solved two or three major mathematical problems that nobody else. And they've been around for a while, so he was. But anyway, he was there. I remember after I read that book, I knew exactly
I know
what
that
happened.
person.
Yeah.
Interesting. So came time, you were wrapping things up. When did you finish up at MIT?
61. So in the summer of 60, I was able to get a summer job at IBM. And one of my professors at MIT, name was Jürgen Moser, was consulting at IBM in the summer in Yorktown, New York. And so partly I got that summer job. I guess got the summer job separately, but he happened to be there. And so we worked on something together that summer. And then when I graduated, I knew that was a good place, so I applied there. Got a job at Yorktown, IBM research at Yorktown.
And is that because you were familiar with the place? Is that did you have a clear idea about what you wanted to pursue in terms of a career at that point?
Yeah, again, it's mathematics and computers. IBM is a computer company. But I did see that I went into their mathematics department, both in the summer and later, and I saw that they gave you really complete freedom almost to at that time to do whatever you wanted to do. And in the research, you kind of picked out your area. So it was a great combination. I knew the environment and everything, so it was just an obvious place to go to next.
So what did you dive into? You started there in 61, 62?
Yeah.
And
well, I was in the math department, and so they said, do good mathematics.
do good work.
Do good work. And so I finished up work that I'd started with Jürgen Moser in one summer, and we put it together, polished it, made a big paper called A Theory of Nonlinear Networks, and it was published in the Journal of Quarterly of Applied Mathematics, I think, and in two separate it was a big long paper. So I did that. That had to do with writing the equations for electrical circuits in a different form and proving things like stability of the transient solutions and things like that. So it was a pretty major piece of work. And then I continued looking at differential equations of electrical circuits and writing, doing papers and research on behavior of circuits.
So was there sort of particular sort of problems that engineers or whatever were facing for which these were solutions? Were these helping people just to understand the behavior of circuits better? how did you get linked into, you know, the...
Well, at the beginning, there was no particular direct application to anything. It just, these were interesting problems, and the fact that you could rewrite the circuit equations, these are the transient equations, in this form was completely new and useful for proving properties, but you know, I don't know that anybody had a problem where they wanted to prove stability or something like that directly, but it was more of a mathematical thing. But that kind of activity led into the next phase.
You can do formal verification before
No,
at a circuit level, right?
Yeah, the simulation, yeah.
You could verify that it was stable or not stable, or...
Well, yeah, you could simulate it. Even back then, the simulators were not very good. The state of being able to simulate anything was just pretty bad. And you know, I remember, you know, in around 65, 4 or 5 or 6, there were problems where people in IBM could not solve like a 3-transistor circuit because it was kind of, it had a special property that, you know, people didn't understand.
Yeah.
And so the state of simulators back then was just, you know, pretty primitive. They could do linear circuits, but nonlinear was a problem. So that got into the next phase of.
Yeah. So after this first activity, what was the next thing, and when did you start? When did you get tied into some practical?
Well, I think in about '64, we got involved in solving linear equations, and linear equations came from circuits. And so the first thing was to be able to solve very, very large linear systems of linear equations, but they were very sparse. They're coming from circuits, so the connectivity was just kind of locally at the nodes and so forth. So this is when we did some initial work in solving sparse matrices, linear systems of sparse matrices, and that led us into simulating electrical circuits, and so. At around 66, we started putting together a new program which would, it's sort of like SPICE, but we were kind of several years earlier than that. It became a program in IBM called ASTAP, which was their circuit simulator, and was used for maybe 30 years.
So did somebody come to you or your department with this problem? Did you sort of go out and discover it? Is it just things you sort of stumbled upon as you were doing interesting mathematical things? What was the...
I remember talking to a group in Poughkeepsie, and they had this problem of simulating a small circuit, and they came to us and said, "What's going on here? We can't do it." And so we analyzed it and found out that, you know, there were eigenvalues of the problem that were large and small, and so the normal numerical methods didn't work on those things. And so one of the people, I was at that time a manager, and I had about 3 other people. One of them, Werner Liniger, was an expert in numerical methods for solving differential equations. And so our group got into, you know, analyzing what was wrong and told them what to do, and they did it, and that kind of got us into this field after that. So we started, you know, you start small and then you kind of take on more and more and more.
So did your group actually build this circuit simulator, or was it others take the ideas and fundamental algorithms and build it? How did that?
We consulted with a group in Poughkeepsie that actually took it and made the program, but they made it. They made the program on our architecture. So we told them how to, you know, solve sparse matrices, what numerical methods should be seen, how to formulate the equations, and for computer solving and things like that, and mapped it out. But they were very, I mean, the success of that program was very much due to that group being able to go out into all of IBM and holding hands as people tried to use it.
Mm-hmm.
And that
A whole new
was-
different kind of tool than they were used to and had to be.
Yeah, because it's a completely new kind of tool, how to use it, and of course it didn't work exactly right, and so you had to modify things and tune it a little bit. But that thing was a success in IBM because this other group,
Mm-hmm.
there's a guy named Al Jimenez, who I remember was just an enthusiast. He would program this thing and then go out to the users and hold their hands and sort of guide them through using it, and it
Mm-hmm.
became in the end everybody was using it in IBM, and and it was very, very successful too.
Mm-hmm.
So
So you say 67 or so, maybe 5 years into IBM for.
we started that kind of stuff about 5 years in,
Mm-hmm.
and that continued. The development continued for through the early 70s,
Mm-hmm.
and I can't. I mean, we just kept working on it, and there was more. It sort of opened up a box of interesting things to do, and we developed other things along those lines.
Mm-hmm.
But,
So this became known within IBM. Did it get published? Did
Yeah.
that work then get adapted quickly outside, or was that late? How did that?
we published. There was no slowing down. We could publish right away, and so we did. And Spice came along maybe a year after we had published. So we had already published the sparse matrix stuff and the numerical methods and the equation formulation. So I always think that if I hadn't been in IBM and was giving it away, it might have been, A-STAP instead of Spice. But
Right. But so your ideas were incorporated into the initial versions of Spice, is that right? That's became the.
well, people were beginning to publish about sparse matrices, so
Mhm.
I don't know, who got what ideas. We had our own ideas, and we developed things and published it, and I'm not sure what the time frame was between the development of Spice. Maybe they're doing the same thing
Mhm.
at similar time.
Right.
So
Yeah, we had a 40th anniversary celebration of Spice here at the museum
yeah,
when there was an IEEE plaque created as a major milestone, IEEE milestone.
yeah,
That must have been last year or the year before, so it was 72, 73
Yeah.
timeframe was when Spice was first released, I guess. So, so how long was this sort of a major, this simulation work, a major focus of your work, and what was the transition to sort of your next major project?
yeah. Well, that's kind of interesting because so while this was going on, I became kind of second level manager, and so I had a bunch of groups under me, and one of the people working, quote, for me, but but these are PhDs and they all went
Right.
off and did their own thing. He was traveling around the company and looking at different groups, and he was a kind of more of a pure mathematician, but he wanted to do something useful, and so he found a group in Los Gatos. IBM had a lab at
Mhm.
one time in Los Gatos, very nice little lab, and he found a group that was trying to build a computer out of some exotic cells or exotic circuits. So the circuits would be able to implement a larger logic function than the normal AND or NOR,
Mhm.
things like that. So you'd put a lot of logic function into one of these circuits. It was called a cascode emitter coupled logic circuit. It was
Mhm.
where you had an emitter-couple circuit on top of another one, so it's cascoded, and you could, implement logic functions of 6, 7, 8 variables or inputs coming in, and so they had at the time we started talking to them, they had basically built a circuit, a computer from these by hand. No computer
No
help
simulation
at all.
or anything.
Right.
Yeah.
Well, there was no logic synthesis at all back then. So he looked at their circuit, and he came up with an algorithm that would decide when a logic function could be implemented in one of these circuits. And so as his manager, or second level manager, I had to understand what he was doing, so I listened to him, and I said, well, I'll just program that for you, because he couldn't program. And so I became his programmer.
Reversal of roles.
At the time we were using a language called APL, so you could program things pretty fast. Right. As a kind of prototype code. So I started doing that, and that got me into where you had this problem of, given the logic function, can it be mapped into something? How do you tell if a circuit of a certain type can be mapped into that?
And what year was this then?
This is middle 70s, I think.
Okay.
So
did this also get you out to California, to Los Gatos for?
Once. Once or twice, but the program I wrote was, took in a logic equation and then analyzed it and said whether you could do it or not. And so this kind of notion of taking in a logic function and then doing something with it became the start of something that grew bigger. So at the beginning, I had a little program that would take up to 8 variables, and they were called A, B, C, D, E, F, G, and it was written in APL. So, and then we said, oh, we need more variables, because things are getting bigger and so forth. And so then we got up to 26 variables, A to Z. And then it expanded more, and so as we were creating this capability, other groups in IBM were thinking about their own exotic circuit and how it could be faster and smaller if we could pack more logic functionality into a single circuit rather than breaking into the smaller ones. And so we started talking to Boca Raton and Poughkeepsie, Fishkill, and so forth, the different groups that were experimenting with how to make computers faster and smaller and so forth. And so this capability, which became 26 variables now, then blew up into many variables. We wanted to do a whole computer, and so this became what I call the Yorktown logic editor, and it was kind of our first step into logic synthesis, and so that's how we got
So
into
was
this.
there sort of a milestone? Did you sort of take these concepts, develop a program which then became widely used within IBM, or was it how it?
No, it's more of a demonstration, and in fact there was another group in IBM led by John Derringer that was doing, they also started doing logic synthesis, and they were more oriented than we were to interacting with the mainframe guys, and so they created they had their own logic synthesis program. They were doing it in a different way, so we had a different way of doing things, and but they made more of an impact than we did inside IBM in terms of actually getting logic synthesis going there. and we made, well, we published everything. We made more of an impact on the outside.
Oh, is that right?
Yeah.
So they were on a path sort of in parallel with your work, is that right? You published.
Yeah, so we had our own, we had.
Was there a rivalry, or was this?
There was a little rivalry, I think. My feeling was that they were more oriented in kind of a people optimization. So you
just looking at
you have
local
a sea of gates, and then you look at a certain area, and you try to make a transformation, and you walk around and do the people optimization. And we had divided our thing into the people optimization was depended upon the standard cell gates you're using at the time. And so you'd have a sea of logic gates, standard cells, and they're connected up in a certain way, and then you would make these transformations on a set of gates and then move it around. So we took a different point of view, and we said, let's do some stuff first that was technology independent. So we don't know what the standard cells are we're going to use or where it's going to go. We just get a better compact view of the logic as logic equations, and then we would then map it into whatever standard cells that were provided. And we were motivated that way because we didn't have one kind of standard cell. We were working with these various groups, and there were cascode emitter coupled logic or cascode voltage things and so forth. So we did the technology independent and then mapping later. So we had a different approach.
I did an oral history with John Derringer a couple of years ago.
Yeah.
So you can go back, and it's posted online. You can see what he has to say on his side of it. I don't remember exactly what his comments were on this particular topic. What was the reception to that? And you said his work got more play within IBM, but how did yours, describe the interaction you might have had with people outside? Did people start calling you up and wanting to learn more?
The people that we talked to had these more exotic circuits, so we had a lot of interaction with them. But we didn't get into the mainframe groups and the main bread and butter of IBM. So we were acting more like a research group, trying to invent new ways of doing things, and then building algorithms and software that would implement these ideas. And so when there's as that effort got started, then we saw that it was building up to a kind of interesting, broader area dealing with logic. How do you manipulate logic and so forth? So we had what I call the Summer of Logic. That was where there were 4 of us who were working together on this at the time. Alberto was at IBM for a year with us, and Gary Hochtel, and Bob Risch, and myself. And we decided, we'll organize the whole thing, and we will divide our group into 4 parts, and we would each have a graduate student come in and work with each one of the major guys, and we would parcel out the jobs. So let's see. Alberto had the 2-level logic minimization job. Gary had the general logic manipulation algorithms. I had the multi-level logic, and Bob Risch had decomposing logic for delay.
And what year was this? What summer of?
I think it's 82. I have to look back, 81 or 82, something like that. So we had this, grand plan for the summer, and we executed it, and it was, amazingly successful. Every lots of new ideas came out, and of course we were all working in logic, so we were sharing logic across the the areas, and ultimately one of the programs that came out was called Espresso, which was a 2-level logic minimization, and we wrote a little book on it that described all the algorithms in detail and mathematical proofs and
so
things
the
like that.
Design Automation Conference was going on at this time. Did you attend that? Is that one of the outlets for any of your work?
I hadn't been attending that, and I forget the first time I went to one of those. It was around that time though, and we had taken the paper. We quickly wrote up something on 2-level logic minimization. The sort of the first Espresso paper, sent it to Design Automation, and it got rejected. So we didn't write it very well. So it was. But that was that paper had a lot of good ideas in it, and so it just took another year to kind of polish it up.
And then it was published, or?
Yeah, it was published, and actually became a little book in fact too.
So yeah, I'm familiar with the name Espresso. Did you did that became a commercial program, or how did that? Did that go out through Berkeley or something? The final. We had a version in IBM. It was an APL version that came out of that summer, but that version became the kind of roadmap for the next version, which was done at Berkeley, written in C, and was distributed freely all over. Oh, I see.
The
Okay.
world, yeah.
All right. So we're now 82 time frame. What was so your initial work focused around circuit simulation.
Yeah.
And then you moved to logic synthesis.
Right.
It's sort of the major area, a lot of peripheral things, I
Yeah.
presume, along the way.
So it was, circuit simulation was continuous variables, and logic was discrete variables, and so there's a major shift there, but all dealing with circuits and computers and things.
So you were at IBM until, what, you started in 61, 62, and you were there for
actually 26 years.
26 years. So you came out in 87. Okay, so we're in 82. So you have another 5 years at IBM. Tell me.
Well, so good question. Good. So things kept building up, and so we added capability to our little logic editor. Capability was layout and placement. So we had during that time the guy who was doing layout and placement was Ralph Otten, and he was from the Netherlands, and he came over and worked for us for about 6 years, and his expertise was in layout. So we added some layout capability at the lower end, some timing optimization at the lower end. So that was when Giovanni Di Michele came to the group.
Yeah.
And then
he came into the group? Or,
well, he was not in our group, but he basically came into IBM research.
Okay.
And was working there for, I don't know how long, but basically when he was there, he worked with us. So, and he'd also been a summer student, is Alberta student. So he was a summer student at IBM as well.
So was any of this work getting out to IBM designers, or was this mainly all people outside of IBM were taking advantage of it?
Well, we were publishing, right? And so I was saying, we built up to finally something we call the Yorktown Silicon Compiler.
Okay.
And
by combining the place and route stuff and along with the logic synthesis.
We added a language. We added some high-level synthesis. So we had high-level synthesis where you could describe things at a higher level, and the guy who did that was Raul Camposano.
Oh, yeah.
So we had that, language, logic synthesis, timing, and layout. So we could start at the top, and we started a project where we'd take the IBM at the time had a RISC computer design.
Just the 801?
801.
Yes.
And so we said, we're going to compile that.
So I was just talking with someone who worked yesterday. I was talking to one of the designers of the 801. And
Who?
Rich Freitas.
I know the name.
He worked on the IO controller. He was a young kid at the time, but he has taken on the task of gathering some of the other designers and project manager to do a joint oral history on the design of the 801.
Oh, okay.
And maybe even have a
That's interesting. I didn't know they're doing that. Yeah.
Yeah, well, that was just yesterday. I mean, we've been sort of working around that, and finally we sort of got him in here, and he agreed to. He had a list of names of people who got somewhere that he's going to try to track down. Several of them are here on the West Coast because they migrated out here to HP or whatever, and a couple of them are still on the East Coast. So he was going to see which ones he could entice to come together and do a joint oral history. So anyway, that's to come, and we'll let you know if that happens.
Yeah, so that's interesting because, when we were doing that, we decided to do the 801. Well, we had to figure out what the 801 was.
Right.
And we had to sign out to check out these documents, which were super secret inside IBM. So we got the manual for that and read through it and figure out what things we had to implement and then do it. So we had to do the, put in the information, describe the 801, and then press the button, and and it would compile. And we actually, did it. And
the target technology was like a Gatorade, some IBM Gatorade technology?
So we had our own target technology, which was I think a differential cascode voltage switch, which again was one of these exotic circuits that you could implement a lot of functionality in a small area. And so as part of the effort was to say, okay, now we have this function. We know we can implement it in a single device. Then we had to lay out the device, with putting the actual layout of the polysilicon and so forth. And Ralph Otten did all that. He figured out how to take the logic equation and make lay it out and make a device that would implement that logic piece. And so that was part of that flow too.
Wow.
So we would on the fly create the logic cell that would be used and I think we tiled it in rows. But it was not a gate array. It was more like
standard cell or
standard cell. Yeah, standard cell. But the cells we got were created on the fly as we did the logic synthesis.
I see. Okay, so this was in. Were you actually able to generate a full 801 or the CPU portion?
We drew a picture.
You drew a picture.
We never used it to make anything and try it out, but we kind of demonstrated.
But you can handle that complexity.
Yes. Yeah,
what was how many gates were we talking about?
I can't remember. They have to ask Ralph Otten. He was, because actually in the middle of that, I had gone to Berkeley for a year on a sabbatical, and I came back, and then we finished it up. But
so this is in 1980.
85. I went to Berkeley, came back for 1 year. 86, and then went to Berkeley. Yeah. So it was reasonable. Complexity.
Absolutely.
That time.
For that time.
Yeah.
Being able to do that kind of thing is.
And I think we did write it up, and it became a chapter in a book by Geiske, and so there's a whole bunch of things. There's one chapter I call the Yorktown silicon compiler, and I think that's a picture of the.
Wow, that really was a
801.
pioneering piece of work
Yeah.
at that time. Sounds like you'd already, Alberto had come to Yorktown there, and you then went and spent a year at Berkeley.
Yeah.
Is there sort of the silicon compiler, Yorktown silicon compiler was, the next major? Is there anything else that you wanted to highlight before we talk about the transition to Berkeley and how that came about?
No, I think we've pretty well covered that. Yeah. So.
Okay. So in the midst of this, in this work on your silicon compiler, and in fact logic synthesis before that, you had established some contact with Berkeley. How was it that Alberto Sangiovanni Vincentelli came back to Yorktown, and you then later went to Berkeley for a year? What?
Okay, so I can't really remember exactly when I first met Alberto, but it was a number of years before that.
Mm-hmm.
And at one time we had a interchange between Berkeley and IBM Research, and we would have a meeting every year, and we would organize it like a little mini symposium, and people would give papers and things like that.
Mm-hmm.
So that was going on for a while, and so there was always this interaction, and I forget. I think Alberto came at the invitation of Gary Hochtel,
Mm-hmm.
who was also one of the major people in this effort. He was a major person in the ASAP development, so
Mm-hmm.
he worked in my group for maybe 15, 20 years.
Mm.
So he was one of my major collaborators over the years. Anyway, I think he knew Alberto even before I did. And so,
Mm-hmm.
actually, Gary got his PhD from Berkeley
Okay.
under
So
Peterson,
you
so
had that
there was a
connection.
connection there. So.
Right.
And I can't remember exactly when Gary and Alberto knew each other.
Mm-hmm.
So. But anyway, Gary invited him to IBM. And when he got there, he was going to be there for a year, and we were doing this kind of logic stuff. And so
Mm-hmm.
we forced him to have to program an APL. And he learned it fine, and so we were all doing that. All that work was done completely in APL, so that was even the layout.
Hmm.
So
So what then led to your year in Berkeley? How did that come about?
why? I guess just because our connection with Alberto,
Mm-hmm.
and at the time IBM Research had this policy, almost like a university, of every 7 years you could have a sabbatical.
Mm-hmm.
And some people took advantage of it, and I had one at MIT in the 60s, and I had another at Imperial College in London, and then Berkeley. So it's kind of doing sabbaticals, and Berkeley was a natural place to go. And
Now, on these sabbaticals previous to Berkeley, did you do teaching at these? You went to a couple of other universities, it sounds
at
like.
MIT I did teach,
Uh-huh.
and this was in the 60s, so
Mhm.
I taught what did I teach?
A long time ago.
A long time ago. It was, I taught a course that Roger Brockett had created on linear control theory, I think it was. Yeah.
So did that, is that something that appealed to you at the time? You thought, could I imagine being a university professor, or is this,
No,
I'm
I
going to do
didn't.
this job and go back to my nice job
Yeah.
at IBM?
It didn't occur that I wanted to do it, and I did the teaching just because that was part of the sabbatical.
Right.
But it didn't thrill me so much. When I was there and came back and went to other places, I
Right.
never thought I would want to teach.
Then you went to the Imperial College in London, you say, and
Imperial College.
what did you taught there as well?
No, I didn't teach there. I was in a research group, and
Okay.
I interacted with a professor there, and we got together and wrote a book called Sensitivity and Optimization. So this is for circuits. So you compute how sensitive the circuit is behavior to variation of parameters. It's like a gradient. So he did half the book, I did half the book, and then that finally came out. That was the first book I actually wrote. So while I was at Imperial College, we worked together basically on this book.
So did either of these, I guess the first MIT was much earlier, but did these sabbaticals serve to spread some of the ideas that you had been developing at IBM? Did you learn, which way did the primary information transfer? Yeah.
Well, I like anything, I guess both ways. So it wasn't, I didn't go there so much to teach courses. I went there to do research in a group, and as part of a group, I knew things, they knew things, and so we exchanged ideas. When I went to Berkeley, of course, we had a whole agenda at that time of logic synthesis. We knew what we wanted to try to get done and so forth. And so when I went there was a big effort in '85. Alberto and myself, Richard, and a bunch of students, maybe eight students who started doing this stuff. And we had marvelously smart graduate students. Rick Rudell, did you know him, or Albert Wang, and these guys were working on this stuff in '85. Yeah. So that was kind of eye-opening because I could see the leverage you could get out of having a good set of graduate students and working together and having ideas and getting them implemented and things like that. So that was.
So what year were you at Berkeley? What?
85.
85, 86, or?
85, 86. Yeah.
So somewhere in here, speaking of logic synthesis, the company Synopsys got started, and some of the people you've described ended up being part of that.
Right. So Art started a company called something in North Carolina called Optimal Solutions.
Optimal Solutions. Yeah.
And I do remember going to a conference there. We had a conference at the. There's a bunch of conferences that were, I guess it was in logic, so it might have been the early IWLS, International Workshop on Logic Synthesis, that was there. Anyway, that Optimal Solutions was there. They had a little closet where it seemed like there were 4 or 5 people there, and they were doing logic synthesis, so we visited them.
Now, had they taken some of their ideas from the previous work you had done? Or
no, Art came in and had worked at GE, I think.
GE, right.
And then got them, apparently they weren't interested in logic synthesis, and so he took ideas that had come from there and started working. It was a completely different set of ideas. And then at one point they decided to move to the Valley, and because of the connections around here and everything. So they moved, and then when these graduate students, we at the time I got to Berkeley, we were working on a system called MIS, M-I-S. It didn't even stand for anything, interactive synthesis or something. But so Rick and Albert, put together MIS, and they programmed it in C, and it was, pretty successful. And then they were hired by this company, which became Synopsys.
Right.
I think when they moved, they may have changed their names.
Right.
But I remember after that meeting, actually the year before, I remember meeting Art at one of these meetings. It was also at North Carolina, and he was in the airport waiting for an airplane, and so I talked to him, and he said he's thinking about starting this company. And my advice was, don't do it. Don't do it, because you'll never get back to research. You start this company,
That might be good.
Anyway, I don't know if he remembers that, but I do. My sage advice.
So did Synopsys ever incorporate the technology which you had created then?
Yes. So the MIS program was
Okay.
up and operational, and the guys who actually put it together and implemented everything, and then I had many new good ideas, were Rick and Albert Wang, and they went and were one of the early
Right.
people who joined IBM or at
Synopsys. Now, one of the other names you mentioned was Raul Campuzano, who also ended up at
right, but
Synopsys.
much later.
Much later, okay.
Yeah.
So, all right. So you had your year at Berkeley, and did the seed start germinating about making moving to Berkeley? Tell me about that process and how you came to a decision.
Not at the time. It was a great experience and so forth, and I guess I learned what it would be like to be at a university, and especially working in the group that was there at the time. So there's a major EDA set of people who were doing EDA, and
Right.
There was Don Peterson and Alberto and Richard and
Albert, yeah, right.
so anyway, that was great. And then, but I didn't think of leaving IBM. And then I got back '86, and in the year '86, '87, IBM started offering early retirement broadly across the company, and so they gave some additional incentive. If you went to a university, they would do other things and so forth for you. So there's incentive to actually leave. and so I'd had the experience at Berkeley, and I thought, well, okay, I can handle that. And but I didn't know where I would be able to get a job offer. And so I interviewed a whole bunch of places, and it was fun interviewing. But in the back of my mind, it was Berkeley I wanted to go to.
Sure.
But job offer was not guaranteed. And not only that, but my wife's from the East Coast, and
that was my next question: is how did your family? You have children by this time, I presume, or?
Well, the children were, already in college.
They were already off.
Okay. The first two had already graduated college.
So they all were born and grew up during your IBM career, and
we were empty nest. But my wife had big attachments to the East Coast, and so going way out here, family and things like that as well. So it was, I wanted to go to Berkeley, but I wasn't sure. So I got an offer from MIT and Princeton and Penn, and of course my wife's from Boston. She wanted me to take the MIT offer.
job, right?
And probably I would have done that, but when I went to MIT that spring, I think it was maybe March or something, to give a talk. They had this major blizzard, and they almost closed the institute there, and so that helped to persuade. persuade that. Yeah.
You must have been used to that. You were working in New York, and then coming from Iowa. I mean, this was just.
Then we've been out to California for a year. So,
yeah, you had that
we had
for
that
a year.
Experience.
So we don't have blizzards here.
Maybe. So anyway, I got the offer from here or Berkeley, and then we came up '87, summer of '87. So it was a big transition.
I'll bet. Yeah.
For me and also for Ruth.
So you came out. You actually ended up retiring from IBM after 26 years, and then you started a new career. I mean, similar field and so forth. What was the?
Well, I told my wife, I was retiring, so I wouldn't work so hard.
She bought that, huh?
A little bit. Anyway.
So what did you think you were coming out to do? Did you come out to be a full professor, to teach? What was the?
Well, I was.
What was the
coming
agenda?
out as a full professor, but I had this kind of half-time professorship, half-time research thing, and so I didn't have to teach, the full
load.
Yeah. And of course, the research part was contingent upon, getting the money and supporting your research. But that wasn't a problem back then. So it was, I say, a major advantage to having a half-time teaching job, because I could continue the research I was doing. And so I came out here, and the first year was a lot of work. I think because the first year, Alberto says, "Well, I'm on sabbatical."
So then, did you have to teach one of his courses?
I had to teach both his courses. No, I had to teach one of his courses, and then I made up a new course in logic synthesis, which was the first time it had been taught. And it was a lot of work, because I wasn't used to teaching, and it was a new experience. But
So it must have been a major cultural transition also, going, even though it's a research institution, and the whole dynamics of Silicon Valley and startup companies and so forth was quite different from the stable world of IBM, I presume.
It was, but back then we were at Berkeley doing a research. So as a research piece, it wasn't that much different. IBM gave you lots of freedom,
Right.
and Berkeley lots of freedom. So the difference was you did the teaching, you had more students around, and then figuring out how to make a Xerox copy of something was a little different.
Do a little more of your own work, huh?
Yeah. So getting used to that environment, but it was great.
So then, what did you dive into? What was the research work that you were doing at Berkeley when you first arrived?
Well, when I first arrived was continue the logic synthesis. There was always a piece here, a piece there.
Always work to be done.
And so, we were doing research and publishing papers. That's how many of those 450 papers got there. We were just publishing all the time, new ideas, new pieces, and so forth. And it was a very, very hot topic in those days. And
Sure.
So that kept up for the next 5 years, and graduating lots of PhDs at the time. And
were you consulting for for Synopsys or Cadence or
So I did some initial consulting for Synopsys. I gave some lectures on logic synthesis, basically a synopsis of the course I was teaching back then. Went down, 2 or 3 times a week, 2 or 3 times a month, maybe something like that, and had some very eager students listening in. And that was that, and so even today, logic synthesis research we're still doing it.
Still working on it, huh?
Yeah, yeah. You can always get, better area, better speeds, mapping into different things.
Mm-hmm. So when did that at least slow down, and did you then start to investigate other areas?
Well, I got into verification.
Okay, so that's the next
that's
major
my
step.
Next and last thing. So, I kept doing the logic synthesis, but
Mm-hmm.
there was a time when we had a talk at Berkeley by a guy from Bell Labs called Bob Kershan.
Mm-hmm.
And he told us about his work on verification. And just one of the lectures that happened, during the week sometime.
Mm-hmm.
And I remember coming out of that lecture saying, this is it. This is the next thing
Mm-hmm.
we should do, verify.
Mm-hmm.
And so in the next, and we got into a kind of an arrangement with Kershan to come to Berkeley every once in a while and help us do some things. And at the same time, there were some developments about how do you represent logic on the computer, and there's BDDs. Have you?
Mm-hmm.
Yeah. And Randy Bryant had worked on and developed BDDs in around '86 and so forth, and they were kind of coming in to logic area.
These are binary decision diagrams?
Yeah. They were coming in, and so we started investigating them initially for synthesis to represent and manipulate
Mm-hmm.
logic equations. And then with Kershan, we saw where we could use those in verification. So we started putting together a verification system. And
Now, what were you trying to verify, and what were you comparing it against?
well, initially we had some toy examples.
Mm-hmm.
Have you heard of the dining philosophers problem?
I think so. I just don't remember that.
You have a circle of philosophers. I don't know why they're philosophers, and they're dining, but they had to. I look at it as they have chopsticks,
Mm-hmm.
but there was only one per person and an extra one, so you could only dine when you had two chopsticks.
Mm-hmm.
Anyway, so then there was some protocol about when you started eating and your neighbor wanted to eat, then you had to pass him a chopstick.
Mm-hmm.
And we had to verify that the whole thing could not stall.
Mm-hmm.
If ever you wanted to dine, to eat, eventually you could.
Mm-hmm.
All right, and so and you could. This was a good problem because you could parameterize it to N dining philosophers.
Mm-hmm.
So we got it going, and we, I remember our joy at being able to prove 6 dining philosophers, something like that, and then we got up to 12 or something, and so we were using BDDs, which was kind of a new thing to
Mm-hmm.
use in formal verification.
Mm-hmm.
And we were using our expertise that we had developed for the synthesis, so it was a natural transition for us.
Mm-hmm.
Then we started building systems that would do verification.
Mm-hmm.
And
So this is all formal verification.
formal. Yeah.
Right.
Yeah.
So you could prove certain properties about some logic network or whatever.
Yeah, or you synthesize here,
Mm-hmm.
and you had the original golden model here, prove they're equivalent.
Right, equivalence model, yeah.
Yeah, so that's a formal verification problem.
Mm-hmm.
In fact, it's not any easier than normal property verification, but
Mm.
but we were motivated by wanting to do synthesis and then proving that we were getting the right answer and
I
not
see.
making errors in the software.
Now, were you consulting, or were there companies that were trying to adopt this technology for products? What was the?
Well, this was quite early in the verification, so there weren't any companies
Mhm.
at that time.
Hadn't evolved to a practical.
And they, as the capability got better and better, then people began to see that, well, maybe
Mm-hmm.
this could be commercially useful.
Right.
And
So this is you arrived in Berkeley in '87?
yeah, so this is like from '92 and well until today. You know, we've been working in verification systems
Mm-hmm.
and seeing the capabilities improving, you know, orders and orders of magnitude
Mm-hmm.
over what was there before.
Now, that improvement come as a result of major breakthroughs in terms of algorithms, approaches? Can you describe sort of a high level where the
Yeah.
major steps or improvements were?
Well, mainly through techniques and algorithms. Like BDDs were the first
Mm-hmm.
thing. They were new to the field, and so they just allowed you to do much more than you ever could. So they were the first breakthrough. And I'd say the second breakthrough came when people started using SAT solvers, satisfiability. So you have a logic circuit, and it had maybe, let's say, a single output,
Mm-hmm.
and you wanted to see if there was an input pattern, and there might be thousands of inputs. That would make a 1 at the output of the circuit. This is called satisfiability.
Mm-hmm.
So either you can make a 1 or it's never possible.
Mm-hmm.
And so SAT solvers started coming in to play in logic synthesis and verification, I guess, at the same time. But I think they're motivated I don't know. I was going to say motivated by the logic synthesis.
Mm-hmm.
There were somehow people who were doing logic things decided that the current SAT solvers were very limited and they could do better. And so there were a series of developments that improved the SAT solvers and then improved and so forth.
Mm-hmm.
So they just became completely flooding the area.
Mm-hmm.
With it. And so I'd say the next breakthrough was this capability of this, orders of magnitude improvement in SAT solvers. And that's actually still continues.
Mm.
And so that was one. And then about 3 years ago, there was another key breakthrough, which was invented by a guy who worked on it at Stanford in his PhD and then went to Colorado. Aaron Bradley is his name.
Mm-hmm.
And this was he called it IC3, and we invented or implemented his idea and kept developing it further. We called it PDR, so IC3 PDR, same thing.
Mm-hmm.
And this was eye-opening. I mean, it was really a brand new way to prove things, and called property-directed reachability,
Mm-hmm.
and became almost a paradigm of new developments.
Now, could you do new kinds of proofs, or did it just handle much larger circuits, or what were the major advantages?
It wouldn't solve all the circuits,
Mm-hmm.
but it kind of almost displaced BDDs.
Mm.
BDDs have this problem of not being stable, so you give it a problem and it just gets bigger and bigger and bigger, the BDD, and so you can't predict that. So it wasn't the most desirable thing, but on some problems it could solve them.
Mm-hmm.
And then PDR came along and kind of displaced that almost completely. At one time I said to my students, no BDDs, and wrote BDD with a cross.
Yeah.
But in the end, there are still problems that BDDs can do that other things can't. So, but SAT solving was one of them. Well, I should have mentioned one other algorithm. So we had BDDs, and then we had interpolation, and SAT solvers were coming in about the same time, and then PDR. So we have this bunch of tools that have come in, and So every year there's a model checking, what they call model checking competition, where a model checking is either property checking or equivalence checking.
Mm-hmm.
And there's been one every year, and you can see this progress over the last 4 or 5 years of the number of problems they can solve, the size of the problems they can solve, and so forth. It's just been going maybe by a factor of 5 or 10 on the last.
Each year.
Yeah, each year.
Mm-hmm.
So that's been really important going on.
Now, have there been companies that have spun out of these
Yes.
ideas? What was the...
Well, let's see. There's a whole bunch of verification companies, and also within the major commercial, like Synopsys has formal verification, Cadence, Metagraphics. Then there's individual companies like Jasper and Real Intent, and I should name all of them, but I can't think of it right now. Yeah, so now most of the startups have kind of struggled a little bit because of the downturn. It was when they started up. I think Jasper is doing pretty well right now. So there's yeah, that.
Yeah, I was involved in EDA during that period, and there was a lot of talk about formal verification for a long time, and it's like when.
Yeah, it's sort of like
when
AI.
Does it become, yeah, when does it become real here?
Right. But it has become real, and there's big advantages in being able to formally verify. But it's a harder problem than it's a harder problem to actually use, because if the problem's too big, you gotta cut it down somehow. You have to chop it up or make some assumptions or things like that, and that's an art. And with the synthesis, you got what you got. You push the button, you get an area and a delay, and maybe you can massage it to get a little bit more, but you don't have to get the right answer. You have to get an answer that's good enough.
Right.
So in some sense, it's easier to use.
Now, you've moved to Berkeley. Did you ever sort of go back and do any collaboration with IBM, or was that?
Yeah. We, in fact, in formal verification, we have a very close collaboration with people in IBM. They're located not at Yorktown; they're located at Austin. IBM has its own formal verification tool called Sixth Sense, and we have dealt with those people for many years. Sometimes we have conference calls with them for once a month, something like that. And they've been very open in sharing information, and we share information. So since IBM doesn't sell a formal verification product,
right,
we can actually exchange good ideas.
Right.
Whereas if you're talking to somebody who's selling a product in that area, it's a little bit more difficult.
A little bit tighter.
Yeah. And also, IBM can give us examples of problems.
Yes.
Whereas commercial companies can't give
much harder.
their customers examples.
Yeah.
So it's much harder. Yeah.
So you talked about sabbaticals at IBM. Have you taken sabbaticals while at Berkeley? And do they have a similar program where you've gone off to other universities or research places?
Yes. Yeah, I took 2 sabbaticals while I was here. One was went to Paris one time for not a very long time, but at the time I went, there was DEC had a research lab in Paris, outside of Paris, and one of my former students was working there. So
you got yourself an invitation. Huh?
I got myself an invitation. Lived in Paris, and then took the train out to the suburb every day. That was fun. And I went to Delft, and that was, again, I got myself an invitation because my friend who I worked with at IBM, Ralph Otten, was a professor at Delft at the time. So I visited his group. And where else? Yeah, those are the 2 that I did.
So how long did it take your wife to adapt to California? Is that, or is she adapted or still?
She's been adapting.
An iterative process, huh?
Well, we have children, back in the East Coast, so we have a condo near where one of our daughter's family lives in Burlington, Vermont.
Oh, okay.
So we can go back there and spend the summer.
Oh, okay.
There, and the other, another son works for Intel in Portland.
Portland.
So we go up there
So you're
very easily.
a little closer to him.
Yeah. And the third son is around here. So.
Oh, well, at least 2 out of 3 on the West Coast, huh?
Yeah.
So the work in formal verification. What are the? I was going to ask you a specific question about that. Has formal verification made a step into sort of the multiprocessor area?
In using them?
Yeah.
Yeah. Definitely. I guess multiprocessors have been more prevalent for the last 2 years.
Mm-hmm.
And so if you look at the model checking competition, they now run the competition on servers that have 4 processors.
Mm-hmm.
And so all 4 are allowed to be used in solving the example problems that they run there.
Mm-hmm.
And so the winners, or the top competitors, are all using multiprocessors.
Mm-hmm.
Yeah. But they're using it not in the deep parallel kinds of things. They're more at the top.
Mm. I mean, just segmenting the problem at the top and then.
Well, you don't segment the problem.
Okay.
So I mentioned you have BDDs and interpolation and
Mm-hmm.
other techniques, PDR, and so as you're attacking a problem, it's not just one thing that will solve it. Sometimes this will be solved by BDDs. This will be solved by so you don't know which one to try,
Mm-hmm.
and you don't. You could say I'll try this one first and give it so much time and then try this one. So
Mm-hmm.
with multiprocessors, you can try them all at the same time. So this kind of parallelism is the parallelism of the algorithms at the top.
Right.
We haven't so far gotten into parallelizing the algorithms at the
Self, right.
at the self, right?
Yeah.
So there's been some effort in trying to do that, obviously, but it's just hasn't panned out.
Mm-hmm.
So one of my students, Sherrod Malik at Princeton, I think he started a project to say, okay, let's try to investigate SAT solving, and implement it as well as we can to understand it, and then try to parallelize it. So they were not so successful in getting something parallelizable, but they were successful in improving the SAT algorithm so much on a single processor that this was one of the big steps,
Mm-hmm.
became one of the big steps in improved SAT solving.
So how much of the problem, as you look forward, is making the current algorithms more efficient or being able to take advantage of multiprocessors? Is it computationally limited versus it doesn't matter how long you run it, it doesn't, there's a class of problems that it won't solve?
It's still computational limited because, in the category of complexity,
Mm-hmm.
these problems are piece-space complete. So,
Okay.
if you, it used to be that, there's what's the complexity one level down for. I'm coming a blank. We have to cut this out of the tape. NP complete.
Okay.
So SAT solving is NP complete,
Mm-hmm.
and if you take it literally, you wouldn't try doing SAT because it's NP complete. Right?
Mm-hmm.
But there are a lot of practical problems you can do, right?
Mm-hmm.
But at the next level, if it's piece-space complete, you would also say, oh, this might be too hard. And yet, that's what we do all the time in formal verification. We know there are problems we can't solve. On the other hand, we know problems that we're trying to solve come from humans, and that's a very small, special category of the kinds of problems you see. It's not a, it's not a random logic function. It's something, and so that helps, and so we know there are problems we're not going to solve. And even though we run it in parallel and use all the algorithms, we're just not going to get there too much. But there are a lot of problems that are specialized that we can't solve. And we can't say, a priori what algorithm will solve it, but we're solving a lot of them. So, and I'd say, the examples that IBM gives us that are reasonably hard, we solve 50–60% of those. In equivalence checking, where you do synthesis and then compare against the golden model, we can probably solve 85–90% of those, even though those are still, piece space hard.
Now, what sort of complexity are those problems?
Piece space hard. I mean, that's the
number of elements or gates or
Oh, how big are they? Well, you can have 10,000 registers and 100,000 to 1 million gates.
Okay, so
and
these
we
are.
can still solve some of these. And others have 50 registers and a few hundred gates, and we can
Still can't solve them.
yeah. So in the end, if you solve them and prove that the property holds or there's equivalence, you have to do a proof. It's a mathematical proof that says that you can't, that no matter how many cycles you go, you'll never get an error on the output. All right, so for infinite number of cycles, you'll never get an error. So you have to do that by some kind of proof, like induction or something. And so it's a computer, but mathematical proof. That's what formal verification is.
Right.
And but it is surprising the size of problems that we can actually solve. Right.
So one last question on the technology is, what about the world of behavioral synthesis? Where does that stand now? And it's another area that we in the industry have talked about for a long time, and curious
so that
as
was
to your perspective on that.
So that was hyped up quite a bit in maybe the 90s.
Yeah, I helped in the 90s. Yeah.
Yeah, and it never paid off. And but it's one of these things where, just like AI, there are parts of it that basically have spun off and they've become very useful. So there are
sort of specialized, narrow applications or whatever, right?
I don't know exactly where it's successful, because I haven't been following that, but I know there are now companies and methods within companies that actually are quite successful in the high-level synthesis. Cadence has a very good effort, I know, because there are a bunch of Berkeley people that have been developing that within Cadence. And there's been some startups that have been started and sold to. I was thinking Xilinx, but I'm not quite sure. But it apparently is one of these things that now is beginning to pay off, and people are
finally getting some traction.
So the original idea that it should be a useful thing is there, because you describe something at a much higher level.
Right.
But it didn't. They couldn't compete with humans. But now there are things where you're putting more and more things together, so maybe it's a different ballpark nowadays.
So in terms of your sort of major technical contributions at Berkeley, then, have we run the course? Are there other areas that, when did you retire from active research? Or
well, I'm still doing it. So I do. I'm what's called a professor in the graduate school. So that is a formal thing that allows you to get research contracts, have graduate students. You don't have to teach, you don't have to be on committees, things like that. But it's sort of going back to the old IBM days where it's full-time research.
Just got to do research, huh?
But now I'm trying to slow down a little bit. But
what does that mean? Does that mean you only spend 4 or 5 days a week there, or what?
Well, I take off the whole summer.
Oh, okay.
But I'm still in contact with my research group through Skype calls and things. When I'm here, I have a weekly research meeting with my group, and then I actually do some programming in Python. And trying out verification, how to. It's sort of orchestration of verification algorithms. How do you know what to do when and how for how long, and putting that together into a Python script, and then using concurrency multiprocessors to spawn off the individual algorithms on different parts.
So you're still deeply involved. You are
I'm
hands-on.
Yeah, I've always been a hands-on thing. Even when I
guy.
was at IBM and programming for this guy who was one of my employees.
So what do you do when you aren't doing this research at Berkeley? Do you have obviously your family, your kids and grandkids and so forth? Are there
kids and grandkids.
major hobbies that you've developed, or what's your not time for those things yet?
Well, I've slowed down physically. I used to play a lot of tennis, and I used to ski a lot. But now, if I ski and fall over, it's hard to get up. And in tennis, I was, my competitive spirit was there, but I couldn't reach the ball. And so I would pull my hamstrings, and so I had to give that up. So I, ride a bike or walk or things like that, and read, do crossword puzzles, Sudoku.
So what is your, looking back at the technology then, what, if you were starting anew, what is do you think the area is sort of ripest for impact or breakthroughs or whatever, if you, at least in the general space, or even different space,
different space.
What would you, what has really
personally, I would probably get into robots, robotics. It seems to be on the cusp.
On the knee of the curve, right?
So if I were younger and had studied it 5 years ago, I'd be really well placed. And I guess even today, that would be a good thing to study. Commercially, one of the things I like even better is astrophysics. But
that's have a huge renaissance, hasn't it? It's just amazing.
What they're discovering is just amazing. It's just fascinating. And every half a year they have this major thing.
Yeah, it's just stunning. I mean, for a while it seemed like things were stagnating, and now it's just an explosion of new ideas and new discoveries.
So
and
the other day, did you read about the inflation?
Yes.
That's incredible. So
the sizes, and both small and large, and the periods of time over which, all of which are unimaginable in terms of what we normally come in contact with.
Yeah. So I did, I used to enjoy physics a lot, and so, but I'm not going to start reading technical physics. But I like these books that just tell us about.
Skim the top.
Skim the top. That's ever read something called QED, which is it's a little book by Feynman on quantum electrodynamics. It sounds very imposing, but you read it and. It's completely understandable. It's not hardly any equations. So that's interesting stuff.
So have we sort of missed any sort of major steps? We sort of covered your major contributions, at least at a high level. We didn't dip down into the 450 papers and 10 books, but
good thing.
Could they all be categorized under the topics that we talked about at a high level, you think?
Yeah, generally, I mean, there's the differential equations and then solving them, and then logic and verification, and most of those are in the category. One paper I wrote was on how do you organize a tennis tournament of mixed doubles, and we called it spouse avoiding round robin mixed doubles.
Did it get, and it got published somewhere?
Yes, in a mathematics journal, because it was tied to a very famous problem by Euler or somebody. I don't know who. I can't remember now, but it was, you have n couples, and there's a man and a wife. And you never want to have the man and wife play with each other or against each other
right.
to avoid arguments.
Yes.
And then the question is, given n, is there a tournament that behaves that way? And the answer is, for n not equal to 2, 3, and 6, yes.
So this sounds like something you could actually have practical application for, people putting together such tournaments, right?
It came when I was working at IBM, and I was in a indoor tennis club, and the manager of the club came up to me and he said, I want to organize one of these tennis tournaments. So I went back to IBM and talked to some really good people in combinatorics, and we got together and we slowly, proved some of the hard cases for, n equal to 10 and 15 and so forth, and built up that until finally we could say, after that, all the things can be solved by this other technique. So it's an interesting paper. I was proud of that a little bit.
Yeah, so I wanted to just wrap up here in terms of, you had said from your own personal view, you find the area of robotics particularly interesting. If for somebody entering college or graduating and looking at the technology sphere, where do you, obviously robotics is something that's interesting. What are the other areas that you think are sort of ripe for exploration and explosion of opportunity and so forth?
Well, I guess anybody will say the biology part, the DNA and so forth, and then some of the synthetic biology. So that might be another field that is going to be here and growing and have a lot of commercial application.
Is any of the algorithms that you've developed in logic, synthesis, and that sort of thing, is there any applicability to any of those in other fields?
Sure, yeah. So, a lot of synthetic stuff is sort of digital in the way that they work, and so, you could adapt some of these tools to mapping into those kinds of things, little cells that do the computing. And there are new technologies that are, people are looking at, and we don't know what's going to work. There's nanotubes and there's spin electronics and so forth. And so I don't know. I think that any technology that would come into play and be seen as kind of moving ahead, you could then work on a logic synthesis system that would adapt and get that as the hind end of doing the mapping. So. And
does Berkeley have a structure that allows the cross-pollination in these areas? And are you involved in any of those?
No, I'm not. I decided about 2 or 3 years ago not to look at anything else.
Your plate was already full enough, and time to wind down,
so many
not wind up.
interesting things to do, even in both of these areas, and that's what my group does, and we have great problems and good ideas. So that keeps me busy enough. But Berkeley has this citrus lab or building that is between Corey Hall and Soda Hall on the corner, and it's dedicated to getting people from different engineering departments together and working on different projects. And that's what this building is there. And CITRIS stands for something in the interest, something in the interest of society.
I see.
So societal problems. And that's been going on, and it seems to be very active. And many of the professors in my department have labs over there, collaborating with some of their colleagues in mechanical or civil or whatever. And I think the robotics people in our department have their projects over there with other engineering colleagues and things like that. So yeah, it's actually Berkeley is quite a good place for this getting together and synthesizing different developments and ideas. So.
Okay. All right. Well, I think that's a great place to wrap up. Thank you, Professor Brayton, for
Thank
taking
you for
the
your questions.
opportunity to
you kept it going.
learn.